Hello everyone, welcome to our channel Wisdom MM. So in this part of the video, which is brain tumor classification using brain MRI images, in this we will be uh, showing how we can build a ResNet 50 uh, transfer learning model, okay, using our brain MRI images, and how we can classify into different classes, 4 classes basically. So we'll walk over through the code, and we'll also show the data set and how we are cropping the images, preprocessing the images, augmenting them for building a robust model. So first of all, I will just show you the images, our training data, right? So this is our folder brain tumor, and here we have 3 folders. As you can see, this is 3 folders we have: training, testing, and crop. Okay. So in training, as you can see, we have 4 classes: glioma, meningioma, no tumor, and PT query. So if you click on glioma, you can see we have around 1321 images, right? All are the brain MRI images. Okay. So this is glioma. Similarly, we have meningioma, PT query, and we have normal cases. So that is no tumor. It's a clean MRI images. Okay, no issues. So this is our training data basically. Similarly, we have testing data. All the classes are there, having around 300 images in each of the classes. Next, what I have done, I have created cropped images and kept it in the data set folder. Why I have done so? Because while training our model, I'll directly use this cropped images, and within this crop we have training and testing divided. So instead of using directly training and testing, which is having full image, right? It is not focused image; it is a raw image, and it also includes the extra part which is not required, right? So we need focused image. So that's why I have created this cropped folder where we have more focused images, means fully cropped images containing only the useful thing, that is the brain part, brain image. Okay. So like that, for every class I have done that. Now comes the main part, that is uh, how I have done the cropping, right? This is important. So what I will do, I will just show you the demo in our main notebook, and then I will show the code which I have actually executed for building this folder, for creating this folder within our local system. And then when I have created this folder within my local system, I have uploaded the same in the Google Drive, and then I'll use the uh, collab notebook for building the actual model, right? Because for that we require powerful GPU. So let's start with our code. Right? So in this, I'll be showing demo of all the things like cropping images, augmentations, and all, how the images look like. So let's start. So first of all, we need to set the GPU and the high RAM. So for this purpose, I have taken Collab Pro subscription, right? Because the Collab Pro, if you take the Collab Pro, your GPU will be more consistent. It will not be refreshed, or your session will not be easily crashed. Okay, so that's why. And for bulky projects, or the projects having more number of images and all, we require this. Okay. Else, if you have a very powerful GPU in your local system, you can use that also. So first of all, we need to mount our Google Pen drive. So I'm just mounting it. So it's done. So now you can see that in my drive I have brain tumor dataset, right? And within that we have 3 folders: training, testing, cropped. Okay. So now what we have to do is we need to execute this. So when we execute this, I'm already mounted the drive. Okay. Now we can see some sample images. Okay. So for sample images, what I have done, I have selected some of the images for each of the classes to give uh, visual understanding of all the classes. So you can see this is glioma, this is meningioma, this is having no tumor, and this is pituitary tumor. Now the question is how we will be cropping the images and how we will do that. So in the first video, I've just given you a brief overview that how we can actually crop the images, what are the steps involved. Here I will show you programmatically how we can do that step by step. So this is our crop image function, which we actually used for cropping the images and saving it into a different folder. So what we will be doing is first we have to find the extreme points of the image. It crops the rectangle out of them. This is our aim actually. So whatever image you will supply, it will convert it into RGB to grayscale. Okay, so it will convert our colored images into RGB to gray color images. Now we'll be applying Gaussian blur. Okay. Next what we are doing is basically we are thresholding the image. Okay, and we are performing erosion plus dilations. These are the image processing techniques. Okay, to remove some kind of noise. Okay, because sometimes we have some noise in the images which negatively impact our model building process. Okay, so that's why we are using erosion, erode and dilate. Okay, and I will definitely make a separate video where I'll be showing all the image processing augmentation techniques. What is erosion? What is dilation? But here you just see that what techniques I'm using. So first I am using erosion, then I will use dilate. I have used dilate. Now the question is, this is done. The image is converted into grayscale. Already it has removed. We have removed the noise from the images. Now the question comes, what next we have to do? So next we have to find the biggest contours. Okay. So by thresholding. Okay. So now we are using CV's function, that is find contours. Okay. And what we are doing is we are using this thresh, whatever we obtained by this dilation, and there is one external, and then we have chain approx simple. Okay. These are the 3 methods we are using within find contours function. We are supplying these 2 parameters. Now comes the grab counters part. So here what we are doing is we are just approximating what the counter is, and in here we are actually grabbing the counters. Okay, and after getting the counters approximation, we are now getting the maximum part. Okay, what is the maximum counter? So here actually we are getting the counter area basically. Okay, and in that way what we are doing is basically we are finding, in the sense we are you can say we are outlining the biggest counter from the image, and then for cropping we cannot crop based on just this outlining. So we have to actually find the extreme left, extreme right, extreme lower and upper points. Okay, Okay. So for that, what we are doing is, after grabbing the maximum contour, we are finding the extreme point, that is extreme right, extreme left, extreme right, extreme top, and extreme bottom. Okay, we get these 4 points, and these 4 points basically important for actually uh, getting the cropped image. Right? Now the question comes that how we will be doing that. Okay. So basically what we are doing is we are adding contours on the images. So for that we need to draw contours. Okay. So we are drawing contours using CV2 image, and for this we are using actual image, supplying the contours which we got, that is C, with these parameters -1 and 0 to 25, 25 and 4. Okay, so it will add actually contours on the image. Then we have to add extreme points. So we are adding extreme points using cv2.circle. Okay, so this is the counter image. On counter image we are adding extreme left point, and for extreme left we are supplying certain parameters like this. Similarly for all the other extreme points. Now we are adding pixels as 0 for actually cropping it, and whatever thing which is coming by applying all the extreme points, okay, we are extracting out. Okay, so how we are doing it? We are extracting using extreme top minus add pixels up to extreme bottom 1 plus add pixels, then again extreme left 0 minus add pixels up to extreme right 0 plus add pixels, means from top to bottom. Okay, and then we are adding pixels and removing pixels. Similarly from left to right we are removing pixels and adding pixels. So like that we will get the crop image. And for just visualizing each and every step, we have this plotted it like this. So how it is behaving actually step by step. So in plot 1, basically the plot 1, what we are doing is getting the original image, that is image. Next we are getting the image contours, that is the finding the biggest contour. Okay. The step 2 is the finding the biggest contour, that is our img underscore cnt, uh, that is basically this part, the contours which we have added right on the image. So now next is the extreme points. So which is this, right? The extreme points, when we added extreme points, all the 4 extreme points on the image. So this is this img underscore pnt, and then after adding the extreme points, we are actually cropping this image, new image, that is this image, after applying all the extreme points and cropping out. So this is the cropped image, new image, like this. This is the crop. So like that we have cropped the image. Okay, so in my local I have done that. So we have applied the same cropping, right? Let me zoom a bit. So same function I have applied in my local, right? And what I have done, I have mentioned the source directory, that is training and testing under brain tumor. Okay, then I have save it as a, or mention it as a directories, because within training and testing we have 4 more directories, right? And so to apply all the cropping within each image, within each class or folder image, so we have to basically iterate over both the folders, and within training we have to iterate the other nested folder or the subfolders. So for doing that, we have taken it as a training directory, and we are listing directory within this training directory. So now we have all the these directories within training directory and with the proper path. So next what we are doing is we have also applied the image size. Okay, so now we can see that we have iterating, right, for directory in training directory. Then we are mentioning the saving path, save path. So that I have told you that what we have done is we have created one cropped folder, and within that we have to we are creating testing and training. Right? So now you can see that we have done that, right? Within crop we are mentioning that within crop and within training data, all the directories we are adding up on which we are iterating, and then we are accessing the images one by one within each directory and applying this crop image function, and then resizing it with this size 256 and saving it within this path. Similarly for test directory. So when you execute this code, you will be getting this crop folder. Then you will be getting like this, and you will be getting all the cropped images. Okay. So that's it. This is the cropping part. Now comes the another good part, that is we have to prepare the image. Okay. After getting the cropped images, you need to prepare basically. So what I have done here, I have mentioned all the labels, which are the probable labels which we need to predict, and we are also uh, uh, initializing these four lists because we are appending files within them. Okay, so Y train and Y test are the labels, actually training labels and testing labels, and X train and X test will be the train and test images in the form of arrays. Okay, so we are iterating over the labels first, and then we are supplying the training path, from which path we need to pick the image with the labels, and then within that path basically we will be accessing each and every image. Okay, applying bilateral filter to remove image noise. Then we are producing pseudo colored image using color map mode. Okay, then resizing it using 200 size, and then after doing that we are appending the images in the X train, and similarly we are appending Y train, that is the actual label with index. Okay. So like that we are preparing our X train Y train. Similarly for test set, that is X test Y test. Now comes the normalization part, which is very important for basically building our model. Else our model will take too much time to basically get the global, get the actual maximum or minimum value. Okay. So here you can see that we are normalizing by dividing simply by 255, right? So first we are converting it into array. The images are converted into array, and then we are dividing it by 255. Okay. So after that, you can see we are getting 5,712 files as a training set. Okay, and 1,311 as the test set. Now just visualize what is there in our training data. So like this we are getting, this is the cropped images. Okay, and the color map is actually changed. Why this color map changed? Because why we have done that, this color map mode, because you can see that after seeing this image you can understand that these are the bones. The bones will be highlighted. That will be easy for getting the actual pattern from the image. While you can see this one, this is quite plain, and here you can see that it's not sometimes dull. The bones are also dull, and the noise have basically the noise which sometimes uh, reduce the visibility of the bones, and in that way we will not get the actual pattern from the image which we are finding. Okay, so that's why we have used this color map mode. Now comes the this part. So first, now what we have to do, we are shuffling it, okay, so that nothing will be more sequential, okay, because we have built the training data, we have used all the folders sequentially, so that's why we are shuffling all the labels and the images, and then we are converting our white and white test, our labels, into two categorical, that is one hot encoding. Okay. So after that, we are just, what we are doing is we are converting it into train test split, okay, like this, x train xval, y train yval. Okay. So why we have done that? Because for building the model, I have told you in the first video that for while building the model, we'll be not using x test or y test, because we will be treating x test and y test as completely unseen. So what we are doing now, we are basically splitting our training set into further 80 into 20, where 80% of the training set will be used for actually training the model and 20% will be used for validating the model during the epochs iterations of the convolution neural network. Okay, so in that way we can clearly, after building the model, we can actually test our model on completely unseen data, that is X test, Y test, training set. So now we can see that our validation shape is 1143. Okay. So we have a couple of good distribution within training and validation set also. Now comes the image augmentation, that is very important. So this is just a demo that what augmentations we can apply, right? But I have not applied all the exact which are mentioned, because during during the model building phase, we found that when we apply all these uh, augmentation parameters, then our model taking too much time and its accuracy is also quite limited, up to 60 to 65%. So later on, we have basically tuned these parameters. We have used certain parameters only, and the values are also bit changed. So for demo purpose, I'm just showing you by mentioning all the parameters how the images will look like. So what I'm doing, I'm creating one preview to folder. Okay, here. So when you just run it, one preview to folder will be created, and from there, what we are doing is we are generating batches. Okay, within demo datagen.flow, and here we are, what we are doing is we are flowing only the first image, that is x is equal to x train 0 means only one image. So for demo purpose, we'll flowing only one image out of this demo datagen image data generator object, and saving it after converting, after doing augmentation, saving it under preview 2. Okay, with the prefix as aug image. Okay. Now, so this is our original image. Okay, and these are the possible augmentations which we are applying. So you can see that we are using vertical flip, horizontal flip. Okay, horizontal flip also we are doing. Okay, so like that, all the augmentations you can see which we have applied here. But actually you can see we have applied very few, because it actually depends how your model is behaving on those augmentations. So we have selected only these four: horizontal flip, height shift range, width shift range, and rotation range. Now after applying it, we are fitting it and calling our model, that is ResNet 50. So for any time when you be building transfer learning based model, you need to specify the actual model, and you need to download the data, basically their weights. So what I'm doing is I'm mentioning that I don't need the top part, the top architecture. So I'm mentioning it as false. Okay, and the weights what I'm using is the ImageNet weights. Okay. And now what I'm doing is all the layers which we have declared using count base. So all the layers within count base we are making it as trainable too, because in that way we will be customizing those layers based on our use case, that is identifying brain MRI images. Now after getting this count base, our base model, we are just applying some global average pooling, some dropouts, and mentioning that we have 4 classes and we are applying softmax, so it will give the probability for all the classes. Right? Now after that we need to specify our this, that is activation function. Adam is performing well in this case. Next comes the compilation part. So because it is a multi-classification use case, so we have to specify categorical cross-head problem. Okay. If it is only a binary use case, then it will be binary cross-head. Okay. So like that, our model is built, and we have just printed the summary. So this is the summary: how many parameters we have, how many trainable parameters we have, and what are the non-trainable parameters. Next, what I am doing is I am mentioning the callbacks, that is model checkpoint and reduce LR, reduce learning rate on flat. So these are very important, and I'm not using early stopping. That's for the reason, because sometimes after getting that the model is not learning well, so after certain iterations or epochs, you can stop the training. But I want my training to run at least till 50 epochs. That's why I'm not mentioned, but you can mention it in here, your early stopping criteria. Okay. So here I'm mentioning that the patience will be 2. So after 2 consecutive iterations, if the validation loss will not be improved, we will be reducing the learning rate by a factor of 0.3. Now we are just quickly checking. So 4569 is our training data, 1143 is our validation data. So now we have fitted, okay, model.fit, and within that we are using augmentation datagen.flow and supplying all the training. Y train batch size is 64. Validation is our X validation, Y validation, 50 epochs, and all that. So when we started the training, we found that initially you can see our validation accuracy was quite low, 23.36, and the model was totally overfitting in the initial stage, and that is true because we'll be started seeing the images. Okay? The model started seeing the images. After that, you can see that we have very good improvements. After, you can see 10 epochs. Okay, it is showing 62.47 validation accuracy, and we can say that after 20 epochs we got the actual accuracy, that is 98.7. But still run it for 50 epochs to get the model stable, and to see whether we should be getting the consistent validation accuracy or not. You can run it only up to 20 or 25 epochs, 30 epochs as you comfortable. Now, as you can see, this is the training curve. Okay, so how the loss started getting reduced. So you can see that initially up to 0 to, let's say, 2, 3, 4 epochs, it reduces constantly, then again it increases, then again it reduces, then again is slightly increased, and after, you can see 10 epochs, it started showing a declining nature, and it declined a lot. Okay, so this is the validation loss, and training loss. Initially it was very calm, but very less, and after 10 or 20 epochs, it remains consistent, while validation loss also came to the equal to the training loss. Epoch accuracy, you can see that after 20 epochs it remains consistent and remains more than 95 to 96, 98%. So this is our training and learning curves. Now comes the actual part, that is loading the best model. So whatever the best weights we have, we are loading it and we're getting the actual trained best model having highest accuracy. So I have saved it in my drive. You can see that it is saved as model res50.h5. Now we need to validate on our test set. This test set, as I told you, it is completely unseen. So within this test, on this test set, our model is getting 98.86% accuracy. That is very good. And if you see class-wise accuracy and other parameters, so you can see glioma is getting 99 precision, meningioma 97, no tumor and pituitary has 100% precision. While recall, you can also see that glioma has slightly less recall, okay, whereas meningioma is higher, 0.99, and it is 1.01. F1 score is also good for all the 4 classes. For no tumor pituitary it is 1.1 and for these two it is 0.98. So it is quite good. Now comes the actual part, that is confusion matrix. So this is the confusion matrix on our test set, right? And here you can see that pituitary, which is almost 100%. So all the 300 cases it classifies 299 clearly, correctly. No tumor, you can see after 405 cases it classifies 403 correctly. That is huge, right? Meningioma, you can see certain mistakes it has done, but it is not that much because majority it has classified correctly. Similar is the case with glioma. While glioma has relatively less accurate in comparison to others, but still you can see that 292 is the actual correction, while 7 it incorrectly recognized glioma cases as meningioma, 1 as no tumor as well. So that is important, and you can see that the model performed really well. So what model we have used? We have used ResNet 50 model. Now comes the RBC plot. So if we see, we have plotted ROC plot for all the 4 classes. So you can see the ROC curve area is ROC curve area is 1.0, okay, for all the 4 classes, and in the end we have combined ROC plot for all the classes, which is again 1.0. Okay, so that is the ideal ROC curve which we generally sort in any use case. Now the last part, that is plotting sample predictions. So here what we are doing is we are plotting our sample predictions from the test set. So you can see that meningioma, glioma, and pituitary. So all the 4 classes it classifies correctly. So these are the sample predictions of all the 4 classes, correct predictions. So we can see that like this it is predicted. So it is somewhat good, and model is also performing very well. Yeah. So that's it in this video. So we have shown you in this video how we have built the model, how we have cropped the images, how we have performed basic preprocessing, image augmentation, right, and how we have built the model, how the model behaves starting till end. Okay, what's the learning curve, what's the validation results, okay, confusion matrix, and in the end ROC curve and our sample conditions. So I hope you like our video, and this code I'll be sharing in my video description, so you can get the code and you can run the same experiment, okay, in at your system or on your Nonradical app account.